In 1900, physics had an answer for what light is, and it was not a guess. Light was a wave. The question was closed. It took 26 years to reopen it and to name the thing that did. Almost nobody wanted it, including the man who started it. Why the wave answer was so hard to doubt. 1803, Thomas Young sends light through two narrow slits. Behind them, bright bands and dark bands. In the dark ones, light plus light has made no light at all. Nothing solid does that. Waves do, a crest canceling a trough. Then in 1865, Maxwell writes down the equations for electricity and magnetism, and a wave falls out of them. Its speed, from two constants measured on a bench, is the speed of light. Light was not like a wave. Light was one. The crack shows up somewhere unglamorous. Hot things glow, a poker, a filament, a star, and the color depends only on how hot they are. There is a formula for that curve, Wien's law, and it works beautifully. Then the measurements push into the infrared, and it stops working. On the 7th of October, 1900, Heinrich Rubens calls at Max Planck's house and tells him the long wavelengths do not fit. Planck works on it that afternoon. Within days, he has a formula matching the whole curve and presents it on the 19th of October. But he has only fitted it. He cannot say why it is true, and for Planck that is intolerable. On the 14th of December, he gives the reason, and he hates it. The formula only works if the oscillators in the wall of the furnace cannot absorb energy smoothly. They have to take it in whole units, the frequency times a very small constant. The constant we now call h. Now the part that usually gets flattened. Planck did not say light comes in lumps. He said the walls do. The lump belonged to matter absorbing and emitting. The light in between stayed a perfectly ordinary wave. He meant it as bookkeeping, to be explained away later. 30 years on he called it, in a letter, an act of desperation. He had a formula that worked and no interpretation, and one had to be found at any cost. 5 years later, a 26-year-old examiner at the Swiss Patent Office publishes 4 papers in 1 year. The first is about light. The title is, On a Heuristic Viewpoint Concerning the Production and Transformation of Light. Heuristic means a guess that is useful. He is flagging it as speculation in the title. And the argument is not the photoelectric effect. He does not start from any experiment with light and metal at all. He starts from entropy. He takes how the entropy of trapped radiation changes when you squeeze the box, compares it with an ordinary gas, and gets the same form. Radiation is behaving like a crowd of separate, countable things. So Einstein takes the step Planck would not. Planck quantized the walls, Einstein quantizes the light, not an accounting trick at the surface, but lumps out there in flight. The famous part is near the end, and it is short. If light arrives in lumps, shining it on metal should knock electrons loose one lump at a time. So an ejected electron's energy should depend on the frequency of the light, and not at all on how bright it is. Below a certain frequency, nothing comes out however bright the light. Above it, electrons appear at once, even from a very dim source. Plot energy against frequency, and it should be a straight line, and the slope should be Planck's constant, arriving from a completely different direction. What follows is 18 years of the physics community saying no, not ignoring it, rejecting it, and for a sound reason. How does a lump of light go through 2 slits at once and interfere with itself? Young's experiment was still sitting there. 1913. Planck and 3 colleagues nominate Einstein for the Prussian Academy. The letter is glowing, then it stops to apologize for him. He may sometimes have missed the target in his speculations. They write, as for example in his hypothesis of light quanta. That is Planck, writing a reference, for Einstein. In Chicago, Robert Millikan sets out to settle it. He is a skeptic about the picture behind the equation, and he means to measure the prediction to a precision nobody can argue with. It is far harder than it sounds. A clean metal surface oxidizes in seconds. So he builds what he called a machine shop in vacuo, a sealed bulb holding sodium, lithium, and potassium, with a knife on an electromagnet shaving each surface fresh. He spends most of a decade on it. By 1916, he has the straight line, exactly where Einstein said, and Planck's constant from its slope to about 0.5%. And he refuses the idea anyway. In that same paper, he calls it the bold, not to say the reckless, hypothesis of an electromagnetic light corpuscle. Because, he writes, it flies in the face of the thoroughly established facts of interference. He had confirmed the equation and still found the picture behind it unthinkable. He was not being stubborn. In 1909, G.I. Taylor dimmed a source to something like a candle burning a mile away and left it exposed for 3 months. The pattern came out as sharp as with a bright lamp. Starve light as much as you like, it still finds both paths. Einstein's prize is held over and finally awarded in the winter of 1922. The citation is worth reading slowly, for his discovery of the law of the photoelectric effect. The law, the equation. They endorsed the line on the graph and said nothing whatsoever about lumps of light. He was not there to hear it. He was on a ship bound for Japan, and the German ambassador collected it for him. In the room instead was Niels Bohr, honored at the same ceremony. And in his lecture the next day, Bohr said the hypothesis of light quanta is not able to throw light on the nature of radiation. What finally breaks it is not visible light, it is X-rays. In St. Louis, Arthur Compton fires them into a block of graphite and measures what comes back. The wave prediction is clean. The wave shakes an electron, the electron wobbles at that rate and radiates again. Whatever wavelength goes in comes out. What he finds in 1923 is a second peak at a longer wavelength, and the shift grows the further round he swings the detector. So he stops treating it as a wave and treats it as a collision. A quantum carrying energy and momentum hits one electron, knocks it forward, and leaves with what is left. Do that bookkeeping, and the shift depends only on the angle and a fixed constant. The incoming wavelength does not appear in the answer at all. That is the tell. What kind of wave produces a shift that ignores its own wavelength? None does. A thing carrying momentum into a collision produces exactly that. Sommerfeld put it into the next edition of his textbook, calling it probably the most important discovery that could have been made in the current state of physics. Bohr still does not concede. In 1924, with Kramers and Slater, he tries to save the classical wave by giving up something bigger. Energy and momentum conserved only on average, never in a single collision. That is testable. If every collision balances exactly, the scattered X-ray and the recoiling electron must appear together. Every time. April 1925. Both and Geiger in Berlin put a counter on each and look for coincidences. They arrive together. That September, Compton and Simon get the same verdict from the directions. Bohr abandons it within months. That is the end of the classical wave as a complete account of light. And after all that, the thing still has no settled name. 25 years in, people are calling it a light quantum, an energy element needle radiation. The name that stuck arrives on the 18th of December, 1926, in a letter to Nature, and not from a physicist. Gilbert Lewis was a chemist at Berkeley. He proposed the word photon, and the theory he proposed it for was wrong. Lewis thought his photon was conserved, a permanent atom of light, never created, never destroyed, only passed around. It is not. Photons are made and swallowed constantly. The idea was dropped, the word was not. 26 years after a lump Planck did not believe in, the thing had the name it still carries. One loose end, the one Millikan was right about. Compton showed light delivers momentum like a particle. He had not shown it never behaves as a wave. Settling that took until 1986. Granier, Roger and Aspect sent light one quantum at a time into a half-silvered mirror, a detector on each side. A wave splits. Both detectors should sometimes fire together. They did not. The coincidences fell below anything a wave is allowed to produce, by 13 standard deviations. Then they sent that same light into an interferometer, and the fringes came straight back. It never splits at a mirror. It still interferes with itself. Both are true at once, and that is not a paradox waiting to be resolved. It is the answer. A photon is not a tiny wave and not a tiny bullet. It is one unit of excitation of the electromagnetic field, the smallest amount of light that can exist at that frequency. A fact about counting, not about shape. Wave and particle were never the two options. They were the only two pictures we already had words for, and light was never obliged to be either. In 1900, Max Planck wrote down a lump he did not believe in and spent years trying to explain it away. It was the first true thing anyone wrote about light.